Salam and welcome everyone. So today I am just compiling a bunch of shorter videos from my channel for any student who is reviewing your physical chemistry for an exam or for a test. The goal of this video is for you to review the examples that I've done already on this channel from the physical chemistry Atkins textbook. It is to help you in your journey through physical chemistry, whether you're about to take a test or whether you're doing a bunch of problem set. I wish you guys all the very best. Please enjoy the video. Salam. Salam and welcome everyone. So today we're going to be working on the question on the screen that says use the van der Waals parameters for hydrogen sulfide in the resource section to calculate approximate values of one, the Boyle's temperature of H2S from the formula TB equals A over RB, where TB stands as the Boyle temperature, A as well as B are van der Waals parameters, and R is the gas constant. And then we have a second question where we're asked to calculate the radius of an H2S molecule regarded as a sphere. So to start this, rereading the question, we're told to use the van der Waals parameters of hydrogen sulfide in the resource section of the textbook. So the textbook I'm using is the Atkins Physical Chemistry 11th edition textbook. And in the resource section of the textbook, we have the value for A. So the van der Waals parameters that involves attractive forces. It is 4.8, sorry, it is 4.484 atmosphere, okay, dm6 per mole squared. That's the value. And then the value for B, the van der Waals parameters that involves volume, is just simply 4.34 times 10 to the power of negative 2 dm cubed per mole. So these are the values. So from these values, we're asked to calculate the approximate values of the Boyle's temperature. We know the Boyle's temperature formula to be what they've given us, which is just simply TB, okay, equals A over RB. So what we just have to simply do is to substitute. So we know the value for A. So we have 4 point, I don't know why I keep saying 4.84. So we have 4.484, okay, atmosphere dm6 per mole squared, okay, and then we've got R, which we're going to be using 0.08206 dm cube atmosphere per mole Kelvin. Now I want to quickly mention something. We know we have two different gas constants. We have the 8.3145 with the units, and we have the 0.08206. The 0.08206 is used here because the unit matches the unit of this gas constant 0.08206 matches the van der Waals parameters. If we had the questions that involve joule, then we're going to use 8.3145 joule per mole Kelvin because the unit would match the question that we're given. So that's just the reason why. So that would be times the value for B, which is just 4.34 times 10 to the power of negative 2 dm cube per mole. So that's it. So of course, we're going to cancel out the units. We're going to cancel atmosphere, cancel out mole, cancel out 1 mole from the mole squared, and then cancel out the second mole and cancel out the squared. And then, of course, you cancel out dm cube. If you go into dm cube, in dm6 is just going to have dm cube left. And then the other dm cube cancel out the other dm cube. So what we have is just Kelvin, which makes sense because we're solving for the Boyle's temperature. So we have all of that information down. So we're just going to rewrite what we have. So TB, okay, equals 4.8. Sorry, I don't know why I keep saying 4.8. I don't know what's wrong with my brain. 4.484, okay, divided by 0.08206, okay, times 4.34 times 10 to the power of negative 2, and then you have kelvins here. So that is how it's done. Kelvin, of course, the units for temperature. So now you just have to input all of this information in our calculator. So when we input this information in our calculator, we get the Boyle's temperature to be 12.59054 times 10 to the power of 2 kelvins. Of course, rewriting this temperature, the Boyle's temperature will be approximately 12.6 times 10 to the power of 2 Kelvin. So this is basically the answer to this question right here. The answer is this: 12.6 times 10 to the power of 2 kelvins. Yep, that's the Boyle's temperature. So remember, the reason why I have approximately to 3 sig figs is because in chemistry, you have to look at the value with the lowest number of sig figs and use that sig figs as the number of sig figs for the final answer. So we have this A value to be in 4 sig figs. We have gas constant It's a constant, so we're not really focused on that. And then we have the b value to be in 3 sig figs. So hence why I put this second answer, sorry, why we put the final answer in 3 sig figs. So that would be 12.6 times 10 to the power of 2 kelvins. Now we're not done. The second question asks us to find the radius of H2S molecule regarded as a sphere. So solving the next question, let me use the red marker. We're asked to find the radius of H2S molecule. Now, it's important for you to know when you're dealing with van der Waals gas that the formula for finding radius regarded as a sphere is B approximate equals 4 times the volume of the molecule, okay, times Na, where Na is the Avogadro's constant 6.022 times 10 to the power 23 per mole. Okay, we have the volume of the molecule. In this case, the volume that we're dealing with is, in this case, the shape of the molecule is a sphere. Remember, they said the radius of an H2S molecule regarded as a sphere. So we're going to be using the volume of a sphere. So the volume of the molecule is going to simply be 4 over 3 pi r cubed. And then the b value is what we already have, which is just the 4.34 times 10 to the power negative 2 dm cube per mole. So we have that as well. So we have 4.34 times 10 to the power negative 2 dm cube per mole. Now I want to quickly mention something. You're going to be wondering in this question that, okay, what is going on here? Why is it that we have this value? Why is it that we have this formula? It's important for you to know that in the ATKINS physical chemistry textbook, this formula was actually derived. And I hope in a future video to derive this particular formula so that it's not going to be confusing for anyone and everyone can actually like answer questions. So right now, all you have to do is just memorize the formula. But just know if you have the ATKINS physical chemistry textbook, it was explained in the textbook how you would derive this formula. But for right now, just know and memorize this formula for the questions that you're working on. So I'm glad that is over. So we're just going to substitute and reuse the formula in order for us to like solve the problem. So you have B changing to purple now. So you have 4, the volume of the molecule, you substitute. So that'll be 4 over 3 pi r cubed. Okay. So, and then Na, which is just the molecule. So you have B. This, so 4 times 4 is 16. So you have 16 over 3 pi r cube Na. So the next thing you have to do is for you to rewrite this formula, okay, in terms of what we're solving for. So in this case, I'm going to rewrite this formula in terms of R. So when we do that, I'm not going to write the breakdown of how we did it because you guys are taking physical chemistry. So at this point, you're supposed to be able to know how to do it. So you have 3 equals. We're going to, again, solve this in terms of, what they call it, write this in terms of R. So, of course, you cross multiply to do that. So we have 3B, okay. Sorry, let me go back to purple. So you have 3B, okay, when you cross multiply over 16 pi Na. That is how you have the R in the major position of it being alone. So the subject of formula is what I meant by major position. So of course, let's not forget that we have r cube here. So we're going to put out the cube here and say the cube root. And this is the new equation. So all we have to do from here is just to simply substitute. So r is now going to be the cube root, okay, 3 times b. So that will be 3 times 4.34 times 10 to the power negative 2 dm cube per mole, okay, divided by 16 times pi, which is just the value for pi. We know that is 3.142, but I'm going to be using 3.1416, okay, times the Avogadro's constant, which we know to be 6.022 times 10 to the power of 23 per mole. Of course, yeah, so that's how this is done. So let me drag this out a little bit more. So when you have this, of course, we do what we do in math. We cancel out the units to make our work much more easy. And after we've done that, all we have to do is just work on it step by step. So we're going to focus on the numerator first. We have 3 times 4.34 times 10 to the power negative 2 dm cube. When you multiply that, you end up with 0.1302 dm cube. And then we also multiply the values in the denominator. We have 16 times 3.146 times 6.022 times 10 to the power 23. We end up with 302.699 times 10 to the power of 23. So next we have the cube root of what is the division of what is inside the cube root. So when we do that, we end up with 4.29 times, 4.2972. So 4.2972 times 10 to the power negative 27 dm cubed. So when you cube root this value, you have r, there's no longer space. Anyways, we have r is now going to equal 1.6258 times 10 raised to the power of negative 9 decimeter. Of course, we have decimeter and no longer decimeter cube because we've gotten the cube root. So the cubed root of decimeter cube just becomes decimeter. So rewriting this, let's not forget that in chemistry, you're supposed to put your answer in the lowest number of sig figs. And we see the lowest number of sig figs we have here is 3 sig figs because it comes from B, which is 4.34 times 10 to the power negative 2. So we have to put our answer in that. So having our answer, we have R, okay, equals 1.63 times 10 raised to the power of negative 9 decimeter. So this is basically the answer to this question. For those of you who are watching this video, just know that there's another question that I have solved that is very, very similar to this, but the values are different. The molecule is different. So make sure you watch that video. It's going to be linked in the description. Salam and welcome everyone. So today we're going to be working on the question on the screen that says, use the van der Waals parameters for chlorine in the resource section to calculate the approximate values of number 1, Boyle's temperature of chlorine gas from the formula TB equals A over RB, and number 2, the radius of chlorine gas molecule regarded as a sphere. So the first thing you have to note is that we're told to use the van der Waals parameters, but we weren't given. But in the question, we're also told that it's in the resource section of our textbook. Now I'm going to write it from the resource section of the textbook that I'm using, which is just the Atkins Physical Chemistry textbook, the 11th edition. And at the back of the textbook, you have the resource section. So from the resource section, I can write out the A value to be 6.260, okay, atmosphere, dm6 divided by mole square. And then the value for B equals 5.42 times 10 raised to the power of negative 2, okay, dm cube per mole. So that's basically the answer. Yeah, that's basically the values that we're supposed to use. So the first question requires us to determine the Boyle's temperature. So the Boyle's temperature is TB equals A over RB. So that's the formula. All we have to do is just simply substitute. So first of all, substitute the A. So we have 6.260 atmosphere, okay, dm6, okay, divided by mole square, okay, so that's A divided by, so that's the unit, RB. So R, we know that to be the gas constant. And in this question, because of looking at the units, we know that the gas constant that we're supposed to use is going to be the 0.08206 dm cubed, okay, atmosphere divided by mole Kelvin, just because the unit for the parameters that we're dealing with is in atmosphere and is also in dm6, then we know that we're going to be using this. If it's a question where we have a different unit, maybe we had joules or we have pascal, kilopascal, meter cube, then we're going to be using the other gas constant 8.3145. But in this case, we're going to be using 0.08206 because the units match. So times the value for B, so times 5.42 times 10 to the power negative 2 dm cube divided by mole. So cancel out atmospheres, okay? You cancel out atmospheres. You cancel out mole, cancel out mole. You cancel out the second mole, you cancel out the second mole. So you have dm6 and then you have dm cube. Well, cancel out dm cube here, you get, and you cancel out the dm6, you get a dm cube, okay, and then you cancel out this. So basically what we have left is just the unit Kelvin, which matches it because we're solving for the Boyle's temperature. So what you just do next is just simply TB, okay, equals 6.260, okay, divided by all of this information down here because I've successfully removed all of the units. So that will be divided by 0.08206, okay, times 5.42 times 10 to the power of negative 2. And of course, this Kelvin here, when you do the mathematical calculation, is just going to be here. It's going to come up from the denominator because that's what you're supposed to have. So when you input the numerical value here, 6.260 divided by 0.08206, right, times 5.42 times 10 to the power negative 2, TB is just simply going to be 14.0748, okay, times 10 raised to the power of 2 Kelvin. So that's the answer. Now, let's not forget that in our question, we have the values of the van der Waals parameters given to us. We see that this one is in 4 sig figs, this one is in 3 sig figs. So what we're going to do is that we're going to pick the lowest number of significant figures, and that's how we're going to put our value, our final answer value. So therefore, we end up with the three, putting this answer in 3 sig figs, we have 14.1 times 10 raised to the power of 2 kelvins. So that is basically the answer to this. That's how you find the ball's temperature. So that's it. Now the next thing you have to do is to find the radius of the chlorine gas molecule regarded as a sphere. So what you do is for you to note this. Now I wanted to mention, because some of you may be wondering how some of these questions come into play, you have to like review your physical chemistry book and also use my videos as a form of guide to answer those questions. So this one now, so in order for us to find the radius of a van der Waals gas, there's a particular formula you have to use, and that formula has been derived. Although I'm not going to be deriving it in this question because all I want to solve for is the radius. So stay tuned. I'm going to be deriving the formula in future. So just like stay tuned for future videos. So looking at the textbook and basically deriving the formula to find radius is just B with this approximate equals to equals 4 the volume of the molecule, okay, times the Avogadro's constant. So number of atoms. So this is basically the formula you're supposed to use, where B is the van der Waals parameters that we already know the value of. So that's good. We know what the Avogadro's constant is, Na. We know that to be 6.022 times 10 raised to the power of 23 per mole. So that's Avogadro's constant. But then you can be wondering, what is the volume of the molecule? What does Vm stand for? Well, volume of the molecule is simply, going back to our question, we see that we're told that the radius of chlorine gas molecule regarded as a sphere. Well, as the volume of a sphere is just simply 4/3 pi r cube. So we're knowing all of this information. That is basically what is necessary. And of course, we have the value for 4. So let's just write out everything. So writing out everything, we see that we have B is actually going to be equals to, or discretely, you have 4, okay, times 4/3 pi r cubed, okay, Na times Na. So making equation, okay, in terms of RQ, we get R cube, okay, equals 3B divided by 16, okay, pi Na. By the way, pi here is going to be the constant, which is 3.142. So I'm just going to say 3.1416 because I want to make sure that I use as much of the raw value as possible. So it's 3.1416. So we just simply substitute. So you have r cubed becomes 3 times the value for B. Going back up, we see the value for B to be 5.42 times 10 raised to the power negative 2 dm cube. So that would be 3 times 5.42 times 10 raised to the power negative, times 10 raised to the power of negative, 9 raised to the power negative 2 dm cube per mole, okay, divided by 16 times pi, which is 3.1416, okay, times the Avogadro's constant. So that would be 6.022 times 10 raised to the power of 23 per mole. Okay, so of course we cancel out the mole, we input this information in our calculator to just basically get, not the whole thing, I'm going to break it down. So numerator first, so that will be 3 times 5.42 times 10 raised to the power of negative 2 dm cube. That's just simply going to be 0.1626 dm cube. I don't want to rush you guys, that's why I'm breaking it down. And then multiplying the values into denominator, 16 times 3.1416 times 6.022 times 10 raised to the power negative 3. When you input down your calculator, you get 302.699 times 10 raised to the power of 23. So yeah, when you do all of that information, you end up with 0.0005317 times 10 raised to the power of negative 3 dm cube. So that's it. So of course, we do the needful and say r cube. Sorry, not r cube. Now it's going to be r. and then we find the cube root of this value here. Of course, I'm going to rewrite this in a better way. That's going to be 5.3717 times 10 raised to the power of negative 27 dm cube. That's how you do it. Sorry, let me rewrite the cube root. Just cover it all. So when you do that and you input this information on your calculator, you have 1 point. That's so over here you have 1.751 times 10 to the power negative 9. And you see this dm cube, because we do the cube roots, it's just going to be dm, so decimeter. That's going to be the radius. But we also know that because we're dealing with a question in chemistry, we have to put in the lowest number of significant figures that came with the question. We see that the number of significant figures for what we have in the question for the value of b is 3 sig figs. So we use this value and we have to put this answer in 3 sig figs. So you end up with r, okay, equals 1.75 times 10 raised to the power of negative 9 decimeter. And this is the radius to answer this question. So if you're a student who is trying to succeed in all your STEM related courses, make sure you email me at shahabitutorial@gmail.com, because I tutor students in middle school, high school, and college to be the best version of themselves while they're studying STEM in school. So if you're trying to be successful and you want my tutoring and mentorship services, make sure you don't hesitate to email me at shahabitutorial@gmail.com. I wish you guys all the very best. Assalamu alaikum wa rahmatullahi wa barakatuh. Salam and welcome everyone. So today we're going to be working on the question on the screen that says the critical constants of ethane are PC equals 48.20 atmospheres, VC equals 148 centimeter cube per mole, and TC equals 305.4 Kelvin. Calculate the van der Waals parameters of the gas and estimate the radius of the molecule. So PC represents what you call the critical pressure. VC represents the critical volume, or you can say the critical molar volume, because it's centimeter cube per mole that you're given. And then TC represents the critical temperature. So from this information, we're asked to calculate the van der Waals parameters. So A, okay, that's the van der Waals parameters for attractive forces. And then you have B, van der Waals parameters for excluded volume. And then, of course, we're told to find the radius of the molecule. So that is just simply R. So we're now told to basically, solve it. So the first thing you have to do is this. Whenever you're given a question like this and tell you about van der Waals parameters, we have for you to know that usually the volume unit that we use for van der Waals parameters is decimeter cube. And when we're dealing with molar volumes of van der Waals parameters, usually, every single time we use decimeter cube per mole. So, and again, we have the atmospheres here, and just working with what they call it, the gas constant 0.08206 decimeter cube atmospheres per mole Kelvin, you already know that this centimeter cube is not supposed to be there. So we're going to go from centimeter cube, okay, per mole, to decimeter cube per mole. So that's the first thing we have to do. We have to convert. To convert, we have to remember that 10 centimeter is going to give you 1 decimeter. So 10 decimeter cubed, when you cube it to find what 10 decimeter cube is, since we're dealing with volume and not length, we just simply be 10 times 10 times 10. So that's 1,000. Centimeter times centimeter times centimeter, that's centimeter cube. And then 1 times 1 times 1, 1 decimeter times decimeter times decimeter. So that'll be 1 decimeter cube. So now we have what the standard conversion formula is. Now we have to use the VC value we have. So we have 148 centimeter cube per mole. So I'm just going to remove the mole because it's not going to be useful in this conversion. So I'm just going to say 148, okay, centimeter cube equals to X. So you just simply cross multiply, and then you just have 1,000 centimeter cube X equal 1 decimeter cube times 148 centimeter cube. So when you divide both sides by 1,000 centimeter cube, you end up with, cancel out the centimeter cube, cancel out the centimeter cube, the 1,000, the 1,000. And then, of course, you cancel out centimeter cube here, centimeter cube here. So what this is just going to be is 148 times 10 to the power of negative 3 decimeter cube. So X becomes 148 times 10 to the power of negative 3 decimeter cubed. But then let's not forget that we're dealing with a VC question and it's supposed to be per mole. So we're just going to rewrite this to be VC is now actually going to be 148 times 10 to the power of negative 3 decimeter cube per mole. Don't forget the per mole. The reason why I took away the per mole is just so I can do the conversion, not for anything else except for that. So the next thing you have to know is that they told us what the van der Waals parameters, the critical constants are, and they want us to find the van der Waals parameters. Looking at the physical chemistry Atkins textbook, the 11th edition, you're going to note this, that all of the formulas to be able to find the van der Waals parameters using the critical constants are there. And from the textbook, we have the VC is equal to 3B. So to find what the van der Waals parameters for excluded volume B, we're going to end up with VC divided by 3. So we have the VC, so we're just going to say B is going to be, since it's VC divided by 3, so we have B is going to be 148 times 10 to the power of negative 3 decimeter cube per mole divided by 3. B equals 49.333 times 10 to the power of negative 3 decimeter cubed per mole. So, of course, when you do this, I want to rewrite this in a way where it's like easier. So that would just be not just easy. I also want to make sure it's in three significant figures, because in chemistry, you have to look at the values you use to calculate and see the lowest number of significant figures. And in this case, the main value we were given is just 148 and it's in three sig figs. So we have to have our final answer in three sig figs. You end up with 0.0493, again, three sig figs, decimeter cube per mole. So yeah, that's how it's done. So this is the answer to the van der Waals parameter B. So now we have to find the van der Waals parameter for A. So to do that, we have to remember that there's also a formula to solve this. So looking at the physical chemistry Atkins textbook, we see that the formula to find A using our critical values for ethane, we have just critical values formula. It's important for you to know that you have PC, okay, the critical pressure is equal to the van der Waals parameters A divided by 27B squared. We already know the value for B because we just solved for it. We know the value for PC because we were given. So then we can just simply solve for A. So the value for PC we were given is just simply 48.20 atmosphere. So PC is 48.20 atmosphere. So of course we just simply substitute based on what we have. To find what A is, you can just simply cross multiply. Honestly, let's just do it direct. So we have A equals PC 27B squared. So A is just simply PC's, what's PC again? PC is 48.20 atmosphere. So we have 48.20 atmospheres times 27 times B squared. So that would be 0.0493 decimeter cube per mole, all squared. So when we do this, what you end up with is, I'm going to square this one over here. You have A equals 48.20 atmospheres, okay, times 27 times 0.0493 decimeter cube per mole, all squared is just going to give you 0.0024337 decimeter raised to the power of 6 per mole squared. So decimeter raised to the power of 6 per mole squared. So that is it. So of course you just multiply everything. You end up with A equals 3.16722 atmosphere decimeter raised to the power of 6 per mole squared. Now I wanted to quickly mention this. Let's not forget, we're going to pick the lowest number of sig figs because that's how you work in chemistry. So basically our answer has to be in three sig figs. So the value for A is not just 3.16722. It's going to be A equals 3.17, okay, atmosphere decimeter raised to the power of 6 per mole squared. So this is basically the answer to this question. You have a 3.17 atmosphere atmosphere decimeter raised to the power of 6 per mole squared, and that's basically the answer. Now the next thing we have to solve for is just simply R.
So the first thing you have to do when you're trying to determine R is for you to use the equation that is necessary in order for you to determine R for a van der Waals gas. You have the equation from the textbook, which I'm about to write, as B equal to 4 volume of the molecule times Na, where the value for B is what we solve for. So the van der Waals parameters, which we have solved for earlier, 0.0493 decimeter cube per mole, while the volume of the molecule, we're gonna notes that the molecule is regarded as a sphere. So, a van der Waals molecule, whenever you're dealing with van der Waals gases, just know that the molecule that we're using, we use the volume of a sphere. So the volume of the molecule is just simply going to be the volume of the sphere, since we assume the molecule is a sphere. So that will be 4 over 3 pi r cubed. And of course, Na is just Avogadro's constant, or Avogadro's number, which is just 6.022 times 10 to the power of 23 per mole. So that's basically what you need. So the value for B, let me rewrite that as B equals 0.09, sorry, 0.0493 dm cube per mole. So when you have all of this information, all you have to do is just simply substitute. So you have B, okay, equals 4 volume of the molecule times Na. When you substitute, you have B equals 4 times the volume of the molecule is just simply 4 over 3 pi r cube, okay? And then, of course, you've got Na. So, yeah, I want to quickly mention this before we move further. Note that this pi here is just simply the value for pi that we know, which is just 3.1416 or 3.142. I'm going to be using more of the raw data or raw value. So that's 3.1416. So we're just going to rewrite this equation. So that will be B equals to 16 over 3 pi r cube Na. And next, I would be rewriting this equation. Okay, so let's rewrite this equation. Okay, in terms of r cubed, in order for us to like focus on solving for r itself. In terms of r cubed, so rewriting this equation in terms of r cubed, we have r cubed equals 3b. Okay, so 3 times b, because we would have to cross multiply, so that would be 3b over 16 pi Na. So now all we simply have to do is just simply substitute. So r cube is going to be 3 times b. So b is simply 0.0493. But of course, because we're dealing with chemistry, I'm going to want to use the more of the raw value, not just for me to just simply use the approximated value. So I'm going to be using 0.049333. So I'll put that here. So 3 times 0.049333, and of course, let's not forget the unit, decimeter cube per mole. So and then substitute the rest. So you got 16 times pi is 3.1416, and of course Avogadro's constant is 6.022 times 10 to the power of 23 per mole. So of course you cancel out the per mole and mole, and yeah. So next we have 3 times 0.049333 decimeter cube. We're going to multiply the information in the numerator to get 0.147999 decimeter cubed. Okay, divided by 16 times 3.1416 times 6.0222 times 10 to the power of 23. When you multiply the information in the denominator, you end up with 302 0.6994 times 10 to the power of 23. Of course, we would further we're going to further divide this. So 0.147999 decimeter cube divided by 302.6994 times 10 to the power of negative 23 will end up giving you 4.88931 times 10 to the power of negative 27 dm cubed. Of course, because we're told to solve for radius, we have to find the cube roots of this information here. So I'm just going to simply find the cube roots of the left side and the right side. So we'll find the cube roots in order for us to find the radius. So solving for the cube roots, we have r is going to actually be 1.69726, okay, times 10 raised to the power of negative 9 dm. Of course, because the cube root of dm cube is just going to be dm. And let's not also forget that because we're dealing with a chemistry based question, we have to pick the lowest number of significant figures and put our final answer in that number of significant figures. So looking at this particular part of our question, we see that we have how many significant figures to be the lowest. We see that the value for b, which is the main value that we're given, every other thing, the pi, the Avogadro is constant, every other thing is a constant, so we're just going to focus on b. We know that b is actually in 3 sig figs, even though we use the raw data to determine it. So if you go back to our b value, we know it's in 3 sig figs. That means our final answer here has to be in 3 sig figs. So it's supposed to be stopping at 9. So I'm just going to rewrite the answer to be r, okay, is equal to 1.70 times 10 raised to the power of negative 9 decimeter. So this is the radius of this question. So hopefully I've been able to like explain it properly. If you're confused, make sure you put in the comment section and I'm going to try to answer any questions you may have or just rewatch the video. I also wanted to mention that I actually did another question which is very, very similar to this one and it's going to be on the screen. So make sure you watch that video. It is the exact same type of question, just different values, but still the same material, still the same concept that you're learning. So try to watch that video so that you have like the full picture of this kind of question in your physical chemistry class.
Salam and welcome everyone. So today we're going to be working on the question on the screen that says the critical constants of methane are PC equals 45.6 atmospheres, VC equals 98.7 centimeter cube per mole, and TC equals 190.6 Kelvin. Calculate the van der Waals parameters of the gas and estimate the radius of the molecules. So the first thing you have to know is this. We're told that the critical constants of methane are PC equals 45.6 atmospheres, VC equals 98.7 centimeter cube, and TC equals 190.6 kelvins. The first thing you have to do is for you to remember that PC represents what is called critical pressure, VC is equal to critical volume, and then TC is critical temperature. Looking at the volume in of itself, we see that we're told is centimeter cube per mole. This is not just volume by itself, this is actually molar volume. So this is actually the critical molar volume. That is what this is. And of course, that is basically the information that we're given. And then we're told to determine the van der Waals parameters, which are A as well as B. And then we're also told to estimate the radius of the molecule, which is just simply R, where involves the strength of attractive forces, and then B involves like information on the volume. So, or excluded volume, something like that. So the point I'm trying to make is that these are the three things that we're asked to solve for. So we can just go straight to solving it, but the issue is this. We are given the volume in centimeter cube per mole. And from your knowledge of physical chemistry, it's important for you to note that whenever you're dealing with molar volume questions, especially when they involve van der Waals gases, we tend to have the van der Waals parameters in decimeter cube per mole and not centimeter cube per mole. So what this is trying to tell you is that we have to convert from centimeter cube per mole to decimeter cube per mole. So we're going to go from centimeter cube per mole. Okay, we're going to do the conversions first before we can start solving to decimeter cube per mole. Okay, so what that looks like is that we have to remember that to go from decimeter to centimeter, we have to remember this, that 10 centimeter, okay, gives you 1 decimeter. So 10 decimeter cube is going to give you how many 10 centimeter cube is going to give you how many decimeter cube. So 10 times 10 times 10 would give you 1000. Centimeter times centimeter times centimeter will give you centimeter cube. And then 1 times 1 times 1 is 1. Decimeter times decimeter times decimeter is decimeter cube. So this is basically the standard for the calculation for conversion. So we've got this, and then we've seen that our information is 98.7 centimeter cube per mole. I'm going to first of all ignore the per mole because we don't need that in this solution. So I'm going to put 98.7 centimeter cube, and I'm just going to call this, I guess, let me just say X. So let's cross multiply. It's going to be 1000 X cube, X centimeter cube. Okay. Or 1000 centimeter cube X, whatever you want to call it. It's just 1 decimeter cube times 98.7 centimeter cube. Cancel both side by 1000 centimeter cube. 1000 centimeter cube. So you cancel centimeter cube, cancel that out. So this would just simply mean X is equal to 98.7 times 10 raised to the power with negative 3 decimeter cube. Now, let's not forget that it's not just decimeter cube, right? It's decimeter cube per mole. So I'm going to write the updated VC to be 98.7 times 10 raised to the power of negative 3 decimeter cube per mole. That's basically how you solve this. Now that we have successfully converted, we can now continue with our work. To go from to determine what A is, we have to go back to our textbook. I'm using the physical chemistry ATKINS textbook, and in our textbook we know that the van der Waals parameters, the formula for the molar critical volume or the critical molar volume VC is actually equal to just 3B. So the parameter B can be found because we know the value of VC. So Finding B, we're just going to have B is equal to VC divided by 3. We know what our VC is because we've been given in the question. VC is 98.7 um, times 10 to the power negative 3 decimeter cube per mole. So we're going to have 98, okay, 0.7 times 10 to the power negative 3 decimeter cube per mole, okay, divided by 3. Now, I want to quickly mention something so no one is confused. I didn't just bring out this formula from nowhere. The Physical Chemistry Atkins 11th edition textbook has the formula for the critical volume in terms of van der Waals gases. So whenever you have a van der Waals gases, there is a formula for VC, just like you have the formula for perfect gas, PV equals nRT. There is the formula for VC, there's formula for TC, there's formula for PC. So the formula for the critical molar volume is equal to 3 times B whenever you're dealing with van der Waals gas, only for van der Waals gas. So, anyways, you have 98.7 times 10 to the power negative 3 decimeter cube per mole. I apologize, not only for Van der Waals gas, but whenever you're doing Van der Waals gas, this is what you use. So 98.7 times 10 to the power negative 3 decimeter cube per mole divided by 3 will simply give you 0.0329 decimeter cube per mole. And this is basically the answer for B. So we've successfully found one of the parameters. Now that we know the value for B, we can go on to solve the value for A. And to get the A, right, we have to use another information, right? The other information we use is the critical pressure. And the formula for critical pressure for a van der Waals gas is A divided by 27B squared. All of this information is in the Physical Chemistry Atkins textbook, and also, yeah, also I believe also the way it's been derived. So yeah, that's it. So this is the formula we're going to use. B PC is equal to A divided by 27B squared. Don't forget we have the PC value. We're given that in the question. We have the B value. We've solved for that. Now all we have to do is find the A value. So that's just going to be, we're going to now like substitute. Okay, we're going to substitute the values we have to determine the unknown value A. So we see that PC, let's go back, is simply 45.6 atmosphere. So I'm just going to put 45.6 atmospheres, okay, equal to A divided by 27 and then B squared. So we're just going to say 27 times 0.0329 decimeter cube per mole, okay, all squared. So that's basically how it's done. So 45.6 atmospheres is equal to A divided by 27 times 0.0329 decimeter cubed squared is 0.00108 decimeter raised to the power of 6 divided by mole squared. Don't forget, we have all of this information, including the units in squared. So all you have to do now when you have this information, so in order for us to determine A, is just to simply cross multiply. So when you cross multiply, you have A is just going to equal 45.6 atmospheres times 27 times 0.001082441, and whatever that is what you get for the value of A. And when I multiply that in my calculator, what I end up with is 1.33266, okay, ATM DM6 per mole squared. So this is basically the answer to the question. But our work is still not done because it's just still not done. The reason why it's not done is because in chemistry, anytime you're given a chemistry question, you have to put your final answer in the lowest number of significant figures for the values in the questions you were given. So you have to go back to the question. We see that PC we're given is in 3 significant figures. We see that VC is in 3 significant figures, and we see that TC is in 4 significant figures. So we have to put our answers in the lowest number of significant figures that we're given. So you see here in B, we have 3 sig figs, 0.329. Now, for A, we have to put our answer in 3 sig figs because that's the lower number of significant figures in the values of the question that we're given. So A is going to be 1.33 atmosphere dm raised to the power of 6 divided by mole squared. So this is basically the answer to this question. Now, we have one more question to go. Remember, we're asked to determine A, B, and R. So the first thing you have to note is this. I'm also going to pull up another formula from the textbook that you need to solve this question. If you're asked to find the radius of a molecule of a van der Waals gas, you have to use this equation here, which is just B, the van der Waals parameters for excluded volume, equals to 4, okay, times the molecule's volume, or the volume of the molecule, times the Avogadro's constant, or number of atoms. So that's the Avogadro's constant. It's important for you to know that the molecules are regarded as spheres. So the volume of the molecule is actually just going to be 4 over 3 pi r cubed, which is just simply the volume of a sphere. That's the first thing. Then the Avogadro's constant. Of course, if you guys have done general chemistry 1, you're not supposed to forget that this is just 6.022 times 10 to the power of 23 per mole. Okay, that's it. And the value of B is whatever you've calculated, which was already solved over here to be what? 0.0329 decimeter cube per mole. So I'm going to write that 0.0329 decimeter cube per mole. Now, I'm still not done. You see, we have the VB value. We know what the volume is going to be. We also know what the Avogadro's constant, or number of atoms, is. We also have to remember that here we have pi. We have to use the value for pi. And the value for pi that we're going to be using is just simply pi is equal to 3.1412. So now that we've gotten all of that information, we just simply substitute. So let me kind of separate this. So you have B like this for V molecule Na. So that would be B. That would be 4 times the volume of a molecule. That would be 4 over 3 pi r cubed. Okay. Na. So B was just simply 4 times 4 is 16. So that would be 16 divided by 3 pi r cubed Na. So of course, since we're trying to solve for the radius, we're just going to rewrite this equation in terms of the radius. So we rewrite this equation above. So this equation right here, we're going to rewrite it in terms of r cubed. So rewriting this equation in terms of r cubed, what you end up with is just simply r cubed. Let me write it here. So it's a fresh page, equals to 3b, okay, divided by 16 pi Na. So this is how you get it. That is basically the work. So since we have that, we just simply substitute, right? So r cubed is just going to be 3, okay, times what is B? 0.0329 decimeter cube per mole divided by 16 times 3.1412 times Na, which is Avogadro's number, 6.022 times 10 to the power 23 per mole. 6.022 times 10 to the power of 23 per mole. So this is how you do this. So of course, let us cancel out the per mole, cancel out the per mole. You have decimeter cube. So you just have r cube is just going to equal 3 times 0.0329 decimeter cube. When you multiply the numerator, you have 0.0987 decimeter cube. And then you divide by what is in the denominator. You multiply 16 times 3.1412 times 6.022 times 10 to the power of 20 times 10 to the power of 23. When you multiply that, what you end up with is 302.7 times 10 to the power of 23. Yeah, that's it. So now, of course, you put this information in your calculator and do the division again. So r cube is just going to be 0.0987 dm cube divided by 302.7 times 10 to the power 23. When you put down your calculator, you end up with 3.261 times 10 to the power of negative 27 decimeter cube. Now we can just simply determine the value for r by taking the cube root of this information here. So we input this 3.261 times 10 to the power of negative 27 decimeter cube. When you take the cube root of that, you have r is equal to 1.48292 times 10 to the power of negative 9. When you take the cube root of decimeter cube, what you end up is just going to be decimeter. So this is the answer to this question, honestly. But our work is still not done because in chemistry, you pick the lowest number of significant figures given to you in the question. So looking at our work, we see that we have B to have 3 sig figs. You have values of pi, You have value for Avogadro's constants. Those are constants, so we don't really take that into account. But the value that we solved for was in 3 sig figs, which is the value for B. So we're going to put our final answer in 3 sig figs. So what you end up with is R is equal to 1.48 times 10 raised to the power of negative 9 decimeter. And this is basically the answer to this question.
Salam and welcome everyone. So today we're going to be working on the question on the screen that says a certain gas obeys the van der Waals equation with A equals 0.76 m raised to the power of 6 Pascal divided by mole squared. Its molar volume is found to be 4.00 times 10 raised to the power of negative 4 meter cube per mole at 288 Kelvin and 4.0 megapascal. From this information, calculate the van der Waals constant B. What is the compression factor for this gas at the prevailing temperature and pressure? So this is a question from the physical chemistry Atkins 11th edition, and as you can see, this is just a standard question. But of course, there's a lot of information. So the first thing you have to do is to write out all of the parameters. We're told that the a certain gas obeys the van der Waals equation. So we're dealing with the van der Waals gas here, and we have the A value. So one of the van der Waals parameters to be 0.76 m raised to the power of 6 Pascal divided by mole squared. We know the molar volume Vm because they said it is 4.00 times 10 raised to the power of negative 4 meter cube per mole. We know the temperature is 288 Kelvin. So temperature is 288 Kelvin. We know the pressure is 4.0 megapascal, or times, you can just say times 10 to the power of 6 Pascal. Okay, that's what mega is. From this information, calculate the van der Waals constant B. So basically, with all the information we have to determine the value for B. We're also asked to calculate the compression factor for this gas at the prevailing temperature and pressure. So we also asked to find the value Z. So yeah, that's it. Determine B and determine Z when you've been given all of this. Before we can go ahead, the first thing I want you guys to note is this. For a van der Waals gas, we have to use the van der Waals equations of state, which is just this information here, or this equation, which is P equals RT. So P as in pressure, R gas constant, T temperature, divided by the molar volume minus B, okay, minus the parameter A divided by the molar volume squared. So this is the equation or formula we're going to be using to determine B. First of all, we have to remember that we have the value for pressure. We're given that, so thank God. We have the gas constant because it's a constant. We have the value for temperature. We have the value for A. We have the value for molar volume. So all really what we have to just do is to substitute all of this information and to determine what B is. So yeah, that's how what we're gonna do. So let's start. So to find B, we can just rewrite the equation as P plus A over Vm squared, okay, equals RT divided by Vm minus B. So pressure would just simply be 4.0 times 10 to the power of 6. So megapascal, or times 10 to the power of 6 Pascal. But I want to quickly mention something. I'm not going to be using the Pascal when I'm solving this because Pascal is the unit for pressure and I cannot cancel Pascal out like that. So I'm going to be using Newton per meter squared, which is another way of writing Pascal. Of course, Pascal unit for pressure. Pressure is force over area, hence why the unit for force Newton, the unit for area meters squared. So I'm going to be using this here, Newton per meter squared. So just make sure you note that because it's not going to be easy for me to be canceling out Pascals. So let me put Newton per meter squared. Okay, that's how it's going to be for everything. So Newton per meter squared, so that's the units for pressure. So I'm just going to put PA here for Pascal so you guys know what's going on. So then you have plus A. What is A? We know the value for A here is 0.76 m raised to the power of 6. So that's meter raised to the power of 6. And then Pascal. So I'm just going to say Newton per meter squared. Okay, that's another one. Per mole squared. So let me put per mole squared, okay, divided by Vm squared, the molar volume squared, which is just 4.00 times 10 to the power of negative 4. 4.00 times 10 to the power of negative 4 meter cubed per mole squared equals R. So R is Yeah, R is just the gas constant. We're going to be using this particular gas constant here. We're not going to be using the 0.08206. We're going to be using 8.3145, okay, meter cubed, okay, Pascal. But of course, we're not using Pascal. We're going to be using what? Newton per meter squared, okay, per mole Kelvin. So per mole Kelvin. Let me write Pascal up here so you guys know what is going on here. Don't worry, like when we're past this point, you guys will have more confidence. I'm just substituting. It's just that values are big and the units are a little bit what they call it, it's a little bit complicated, but it's not hard. Anyways, temperature, we know the value for temperature is just 288 kelvins. So I'll put 288 kelvins here. So I'm done with the numerator here. I'm now going to say divided by Vm minus B. So the molar volume is just simply 4.00 times 10 raised to the power of negative 3 and then meter cubed, okay, per mole, okay, minus B. So that's it. That's really it. That's the first substitution. So now we try to break down information so that it's like easier for us to calculate. So that's what I'm going to be doing next. So yeah, that's what I'm going to be doing next. So rewriting this again, we have, let me change the color. Maybe it's going to be easier to, so that we can easily differentiate. So you have 4.0 times 10 to the power of 6 Newton per meter squared plus 0.76 meter raised to the power of 6 Newton. So sorry, I apologize. Let me rewrite this. Newton per meter square. Newton per meter square per mole squared. So let me just say mole raised to the power of negative 2. Okay. Just to make things easier. Divided by 4.00 times 10 to the power of negative 4 all squared is just the same thing as 1.6 times 10 to the power of negative 7 meter. So m cubed squared is the same thing as m raised to the power of 3 times 2. So 3 times 2 is 6. And then mole squared is the same thing as mole times mole, which is just mole squared. Of course, you know that mole raised to the power of negative 2 and and let me just rewrite this. I apologize. So m raised to the power of 6 per mole squared can also be written as mole raised to the power of negative 2. So yeah, that's it. So we can start like we can start cancel stuff out honestly. So you have mole squared here, you can have mole squared here, you have m raised to the power of 6 in the numerator, you have m raised to the power of 6 in this numerator as well. So I have made this part of our work easier. So I'm just gonna say equal to, let's go on to the other side, 8.3145. So going to the other side, I can say 8.3145 meter cubed Newton per meter squared times 288 Kelvin. So I'm going to multiply this value and this value together. And when I multiply them, because of course we're trying to make our work to be simplified. So 2394.576. Okay, we have the meter cubed Newton divided by meter squared. And then you have mole Kelvin here, and then of course you have Kelvin here. And what you can simply do is to cancel out the Kelvins. Okay, you can also cancel out m squared from m cube, would just leave you with m. So here what you end up with would be different. Of course, this is just the numerator. So I'm just gonna have divided by here 4.00 times 10 to the power of negative 3 meter cube minus b. So 4.00 times 10 to the power of negative 3 meter cube per mole, okay, minus b. So this is the denominator. And I'm trying my possible best not to confuse you guys, honestly. So with time, it's going to be easy for you to like digest. So you have 4. So this is the next one. So you have 4.0 times 10 to the power of 6 Newton per meter squared, okay, plus 0.76 divided by 1.6 times 10 to the power of negative 7. When you do the division, you input 0.76 divided by 1.6 times 10 to the power of negative 7 in your calculator. What you end up with is 4.75, okay, times 10 raised to the power of 6 Newton per meter squared equal to 2394.576, okay, Newton meter per mole. So I'll write Newton meter per mole here. Okay. All of this information here divided by 4.00 times 10 to the power of negative 3 meter cubed per mole minus B. So that's it. That is it. I apologize. I know this is a lot, but it's I don't know, it's chemistry. That's just how it is. So yeah, this is what you have so far. So let me rewrite this again to try and just so it's easier for you guys to digest. So you have 4.0 times 10 raised to the power of 6, okay, Newton per meter squared, okay, plus 4.75 times 10 raised to the power of 6 Newton per meter squared, okay, equals to 2394.576 Newton meter per mole, okay, divided by this information here 4.00 times 10 raised to the power of negative 3 meter cube per mole, okay, minus B. So as you can see, this is better, but we can even make it much more better because we have Newton per meter squared here, Newton per meter squared here. From this, you already know that the units are the same, so we can just simply add up this information. Both of this information can be added up to have 8.75 times 10 to the power of 6 Newton per meter squared. Okay, so the left hand side is okay. And then 2394.576 Newton meter per mole divided by 4.00 times 10 raised to the power of negative 3 meter cube per mole minus B. So that's it. So yeah, we just simply cross multiply. And cross multiply, you just have 8.75 times 10 raised to the power of 6 Newton per meter squared times 4.00 times 10 to the power of negative 3 meter cube per mole. So we're going to multiply that one first. And when we do that first part, we have 3.5 times 10 raised to the power of 4 Newton meter per mole. Okay, that's the first part. Minus 8.75 times 10 raised to the power of 6 Newton per meter squared B equals 2394.576 Newton meter per mole. So that's it. That's literally it. Of course, because this one has the value of B, we're gonna isolate it from this other information. We also have a situation where Newton meter per mole here and Newton meter per mole here. We can just do the addition, or we can just put them or group them together. So when we group them together, we have this situation where you have 3.5 times 10 to the power of 4, okay, Newton meter per mole, okay, minus 2394.576 Newton meter per mole, okay, equal to 8.75 times 10 to the power of 6 Newton per meter square B. Newton per meter squared, and then of course the B, our variable. So of course, when you do this, you end up with 32, okay, 1,605. By the way, this is 3.4 times 10 to the power of 4, 3.5 times 10 to the power of 4, minus 2,300. So it's just basically 35,000 minus 2,394.576. So you're just going to end up with 32,605.424 Newton meter per mole, okay, equal to this information here 8.75 times 10 to the power of 6 Newton per meter squared, okay, B. So of course you guys know what's next because you've been doing math your whole life as chemistry majors. Well, you've been doing math your whole life, and then for chemistry major you should know this. It's just going to cancel both sides by 8.75 times 10 to the power of 6 Newton per meter squared in order for you to isolate and determine the value for B. So I'm going to do that here. So 8.75 times 10 to the power of 6 Newton per meter squared. Cancel out this, cancel out the Newton, cancel out the Newton here as well. Yeah, so those are the only things I can cancel out. So of course, when you input this information to our left in the calculator, 32,605.424 divided by 8.75 times 10 to the power of 6. When you put that information in the calculator, you end up getting 0.0037263, and then you've got meter, and then divided by 1 over meter square will just give you meter cubed per mole. So this is basically the answer for B. Now you're tempted, I can see, to just say, "Yeah, I got my answer," and then you move on. But the problem is this: whenever you're dealing with STEM related questions, especially chemistry questions, you cannot just determine the answer. You have to go back to the lowest number of significant figures that is in the initial question and use that number of significant figures to put your answer in to put your final answer. So basically what I'm saying is, if you have three significant figures that is the lowest number of significant figures in your question, that means your final answer has to be in three significant figures. In this case, our lowest number of significant figures is two, because we've got two significant figures here, three here, three significant figures there, three significant figures here, two significant figures. So we have to put our final answer in actually two significant figures. So it's going to stop right here. So I can rewrite this to be B is equal to 0.0037 meter cube per mole, or B equals 3.7 times 10 to the power of negative 3 meter cube per mole. So this is basically the answer to the value for B, the chemistry way, where the two significant figures are the only things we focus on. So of course we have determined B, but as much as you're like, yeah, thank God, finally, our work is still not done because we're told to determine the compression factor Z. So the compression factor Z is just going to be what? Well, when you're dealing with questions like this, especially for van der Waals gases and you have compression factor questions, note that the formula for compression factors when you're dealing with real gases is just PV so pressure times the molar volume equals RTZ. Okay, where R is gas constant, T is temperature, and Z is compression factor. Hence, Z is just going to be simply pressure times the molar volume divided by RT. So that's it. So we're just going to say Z equals, we're going to substitute the value for pressure. So going back up top, we know the value for pressure to be 4.0 times 10 to the power 6 Pascal. So I'm just going to say Newton meter. So 4.0 times 10 to the power 6 Newton meter square, or Newton per meter square rather than Pascal, times the molar volume. We go back up there. Molar volume, we know that to be here 4.00 times 10 to the power negative 3 meter cube per mole. So 4.00 times 10 to the power negative 4 meter cubed per mole, okay, divided by the gas constant 8.3145 meter cubed, okay, Pascal, which I'll just say Newton per meter squared, okay, times temperature, which is just 288, sorry, Newton per meter squared per mole Kelvin. Forgot that part. And then 28, and then temperature is just 288 kelvins. By the way, the what they call it, the compression factor has no units, so you have to make sure you cancel everything out to make sure there aren't any units. Anyways, let's move on. So I have here I've got meter squared, I've got meter cubed here, so this will just remain 1m. Got Kelvin here, I can cancel Kelvin here. I've got meter squared here, meter cubed here, this will remain in m. Since this remains m in the numerator and here also m in numerator, I'm going to cancel m again, I'll cancel m again. Of course, I'm going to cancel Newton because it's a numerator as well as Newton here as well. You've got what's it called, mole in the denominator here, and of course you've got mole in the denominator here, so you've really cancelled out all of the units. Let me rewrite this. Z is not just the numerator, Z is everything here. So yeah, the value for Z is now going to be Z equals 4.0 times 10 to the power of 6 times 4.00 times 10 to the power negative 4. So multiplying the numerator, you end up with 1600, okay, divided by 8.3145 times 288 is just going to give you 2394.576. Of course, when you input this information further in your calculator, 1600 divided by 2394.576 will just give you 0.6682. So this is the compression factor. But then again, we're chemists. We cannot just use this as the compression factor because it's just isn't enough. Like this, sorry, not that isn't enough, but it isn't the correct answer. So we go back to see how many number of significant figures, that is the lowest number of significant figures that we use in calculating this question. So looking at our work, we see that we have two sig figs here, three sig figs, three sig figs. So two sig figs is the lowest number of significant figures. So we're going to approximate our answer. And our answer is going to be in two sig figs. So Z is actually going to be approximately 0.0037 67. So if you have any questions, please leave in the comment section. I'm here to help you and to answer whatever questions, concerns, or suggestions that you may have. If you're a student who's trying to succeed in all your STEM related courses, make sure you email me at shohabitutoring@gmail.com. I help students who are trying to improve and succeed in all your STEM related courses, whether you're in middle school, high school, or college, to succeed and to be the best version of themselves in their academic career. So if you want my tutoring or mentorship services, make sure you email me at shohabitutoring@gmail.com. I wish you guys all the very best. Assalamu alaikum wa rahmatullahi wa barakatuh.